morning to all of you. It's really an honor for me to present my views on persistent and autonomous surveillance of the ocean. And I really would like to thank the conference organizers for the invitation. The activities and ideas that I'm going to discuss are based on the work performed at the NATO Undersea Research Center over the last decade by many scientists and engineers. And I wish to acknowledge in particular Dr. Tom Curtin, who collaborated with NERC since the early 90s when he was at the Office of Naval Research in the United States. After that, he joined the center as a chief scientist and left just a few months ago. I've been acting chief scientist for a while until Dr. Ed Guff, who is here with us, took over the responsibility for this job. I would also like to thank my colleagues, Dr. Alain Maguire, who is the head of the engineering, and the scientists, Dr. Michel Rixen, Dr. Alberto Alvarez, and Dr. John Potter, who contributed significantly to the development of military and civilian application of AUV technology. Maguire and Potter will present papers at this conference on various aspects of the AUV technology. I have divided my talk in three parts. First, a brief introduction of the NERC for those of you that don't know us. Then I just briefly motivate and explain what is autonomous persistent surveillance in our view. And I will conclude with some examples of civilian and military application of these technologies. Due to the short time, I've cut the presentation, but I'm available. I'm here the whole week, and I have many examples that I don't have the time to present today, but I'm available for discussion. Okay. So what is NERC? NERC is the only NATO research center. It is located in La Spezia, Italy. Since 1959, we have conducted research in support of NATO maritime requirements. And we have followed also the evolution of NATO during the years, and at the end of the Cold War, we have ceased to work only on anti-submarine warfare, and we have been asked to promote innovation into the NATO nations. More recently, we have been given the freedom to seek scientific and industrial collaboration and address also civilian problems. So I'm going to show you that these technologies that we are developing are really dual-use technology, both military and civilian application. The NERC facilities. I believe that we have very nice facilities. In particular, the two ships. We operate the only two NATO ships. The small one that you see in the view graph is the CRV Coastal Research Vessel Leonardo, which is a 28 meters long vessel, really suited for the operation of fleets of autonomous vehicles. Our flagship is, of course, NRV Alliance. She is a full ocean-going ship. She has operated in all the seas of the world, and she is probably the quietest ship available in the world. As I said, we have a fleet of autonomous vehicles, both unmanned, undersea, and surface vehicles. We have the capability to build prototypes, and we have extensive laboratory facilities, including computer communication and remote sensing. As far as the subject of this topic, let me tell you a bit more about the type of AUVs we have. We have about 15 different vehicles, ranging from the very expensive muscle vehicle, which is a Bluefin 21 vehicle, carrying a synthetic aperture sonar design and a NERC and specified a NERC, but built by Thales. And this is a very expensive €2 million Euro plus type of vehicle, providing very nice images of the seafloor. On the other end of the spectrum, we have the Folaga. The Folaga is, or a fleet of Folagas. It's a small vehicle, low cost. The price target is 30,000 euros, and it's a modular AUV and glider, so it's an hybrid vehicle. Not only we have underwater vehicles, but also surface vehicles that I believe will be important for the development of persistent surveillance systems. What do I mean by persistent surveillance? If you consider what we have to do in the sea, really, we can divide it in. We want to survey what is there, and then we want to take a decision and intervene and do something. Say we want to find a military target, like a submarine, or we want to track oceanographic features. So we need to observe, understand, and then take decisions. Typically, we are looking at very large areas with complex physical processes. And certainly, in general, we cannot sample sufficiently the environment, both in time and in space, because of the difficulties and the cost associated. In the past, and still now, we have been using ships, manned ships, to take data in the oceans. And that is a very costly process. But now technology is providing new tools that are really changing the game. We now have the possibility to deploy what we call nodes of a network that can communicate among themselves. They have enough energy that they store enough energy that they can stay in the environment for a long period of time. They have intelligence, they understand the environment, they can move in the environment, and typically they are affordable compared with ships, of course, and they are interoperable. These are really a game changer, especially because they can adapt to the environment. And in terms of, for instance, anti-submarine warfare, which is one of our tasks, they really invert the asymmetry. In the past, the submarine had advantages because it was difficult to see, but now a fleet of vehicles around the submarine is, of course, changing and inverting the situation. The vehicle can cooperate together, have adaptive and cooperative behaviors, and they provide feedback to the operators to take decisions. And in this diagram, I'm trying to show you what really I mean. In the diagram, what is in green is what we should know. What is in red, will come later, is what we should do. And in blue are the tools that are helping us in our decision. And so we operate in an ocean, and we need to know and to predict how it behaves. We need to know how energy propagates, how it is scattered, in order to be able to detect and classify a target. And by a target, I mean whatever. It can be a submarine or can be an oceanographic feature. Of course, we know, we have to know the environment and we have to predict, and with this prediction, there are risks associated with it. And in the end, we have to take decisions, we have to intervene. In this process, we are helped by a lot of things. We are helped by in situ data collected by fixed sensors or by mobile sensors. We have remote sensing tools. We have databases, prior knowledge of the environment. They are assimilated into models, and they help us understanding and taking decisions. But each decision each decision has a cost associated with it and a risk. And we want to minimize the cost and minimize the risk. And we do that by a feedback loop. Essentially, what we do is, for instance, in an area we understand that there are not enough data to take a decision, so we go back and we want to collect more data. Typically, this is done, we have a human in the loop that decides what to do. Of course, this is time-consuming and costly. Sometimes the feedback loop is not fast enough. What we want to do, and we are doing, is that we want to take a shortcut and have the sensors, have an autonomous control loop where the sensor understands that there is not enough data, and so they move to the area where the data has to be taken. And this is what we need by persistent and autonomous surveillance of the ocean. By doing that, we increase the response time and we decrease the costs. And of course, all the disciplines that you are familiar with, which are now marked in black on the view graphs, help us in all this process. We have not been doing this work in isolation, of course. This is a work that has been carried out at the center for the last decade or even more. And just would like to mention here three programs that we have been cooperating with and had a significant impact on our thinking. The first one is, of course, the Autonomous Oceanographic Sampling Network, led by Tom Curtin when he was at ONR, and funded by the Office of Naval Research. That ended about 2005 and was followed by a continuation which is called Persistent Littoral Undersea Surveillance, always funded, again funded by ONR, and is still ongoing. On our side, we have funded what we called GOATS, the Generic Oceanographic Array Technology System, and it was a joint research program with MIT, Harvard, ONR, and many other institutions. So you can look in the literature, and much of the work that we are doing now is based on the findings of those programs. Let me now quickly move to some examples of these applications. And the first one that we have done are the seafloor surveys with network of underwater vehicles. I have many examples, but I will just quote one. For those of you who are interested, catch me in the corridors and we can discuss the others. One nice success story has been the survey of the ports in southern Adriatic. In Puglia ports, there are 13 ports that are littered with World War II ammunitions chemically loaded with mustard gas. This presents really a threat to the population and in particular to the fishermen. And when I say littered, I mean hundreds and hundreds of bombs and projectiles that are buried in the seafloor or even on the seafloor, proud on the seafloor. So we have been requested by Italian authorities to use our technology, and in this case we use the Remus vehicles with the dual frequency side scan sonar to map the ports. It was not sufficient, acoustic was not sufficient because some of the targets are half buried in the sediment, some are covered by seaweeds. So we had also to use gradiometers towed by a surface vehicle. And we have covered many of these ports and mapped with acoustic and magnetic and fused the information to find the target location. The target location was then passed to the Italian Navy divers who went and collected the bombs, and you can see pictures of those. This is still going because of the number of the targets that are present on the seafloor. We have, of course, participated to many military exercises, and I'm giving you two examples. One is oceanographic type of example, and the other one is more anti-submarine warfare. This year, in the winter, a Proud Manta exercise took place southwest of Sicily, involving the participation of many ships of many NATO navies. And we were asked to provide oceanographic information, currents, sound speed profiles to the people who were running the exercise. So we deployed a fleet of 7 gliders controlled by a control room located in the center in La Spezia. And these gliders have operated for 3 weeks continuously and traveled about 500 kilometers each, completely unattended. They, each time they came to the surface, and downloaded the data to the control center, and we were transmitting the data to the exercise planner. They have collected more than 1,000 CTD profiles each, and this is about 1 order of magnitude more of what a ship could do, and it's also 1 order of magnitude cheaper than employing a ship. Another thing which is worth noting is the fact that during that period, 2 big storms hit the area. And of course, the gliders didn't care. They operated continuously without suffering from the storms. Another type of work that we have been doing is a series of experiments called generic littoral interoperable network technology. So we are looking at interoperable sensors that detect, in this case, a submarine target. We have done several of these, and this year in summer we will complete the trial with a real target. With the test we have done before were with simulated target. This year we are going to do it with a real target. So the scenario is that we will deploy sensors on the seafloor, and they are acoustics and magnetic sensors. These sensors will detect the target initially, and then through acoustic communication and gateway buoys, they will give the order to a fleet of vehicles to move and try to intercept the target. At the same time, there will be a transmitter, a very loud standalone transmitter, insonifying the area. The targets, the echo reflected from the target will be picked up by the towed arrays towed by the vehicles in bistatic, multistatic configuration. So this is the scenario. The submarine arrives, passes a barrier of those fixed sensors, the barrier gives a warning, the vehicle starts moving, and the source starts transmitting. Echoes are received on the 2 receivers bistatically. They communicate with one another through a network node, which is also a mobile sensor, and they form tracks of the target. The track, they send messages, detection, classification, localization messages to the node, and the node, through surface expression, a gateway buoy, relays the information to a control center. Let me now finish by mentioning the work that we have been doing with, in environmental protection. We are now the only NATO entity which can participate to the EC Framework 7 program. And one of the examples is the Argo Marine project. The scope of this project is to develop and test integrated systems for detecting marine pollution and to monitor the ship traffic for effective interventions in case of marine accidents. We are using, the consortium is using a lot of data from a lot of platforms, SAR, optical, chemical, acoustic sensors, from satellites, aircraft, vessels, in situ buoys and AUVs. And of course, all is tied up by high-speed communication, feeding into a control center where some models are run to, for post-accident intervention and impact prediction. The task that we are performing in this consortium is the development of low-cost autonomous vehicles that are equipped with chemical sensors for detecting oil in the water. So the objective is the integration of this electronic nose, so to speak, to measure the concentration of oil in water. And due to the gliding capability of the Folaga, because we are using a fleet of Folagas, the platform perform autonomously long-term patrol missions. They can stay in the environment for quite a long time. And also we are studying how to best deploy those patrolling vehicles in an area, taking into account that we have also fixed sensors. These are the tasks that we are doing. This is an ongoing project which will end next year. Of course, these technologies are of great interest to the oil industry, especially after the problems in the Gulf of Mexico. It is really attractive to the oil industry that has to respond more and more to stringent requirements imposed by national authorities. And we have collaborated extensively with the Italian Eni oil company and Tecnomare, their engineering company, to test a variety of chemical sensors installed on board our Ocean Explorers. The Ocean Explorers are big vehicles, 21-inch, with a large payload, which is very useful to de-risk new ideas. It's easy to install new sensors and to test them underwater and see whether they work and what capabilities they have. We, as I said, we have tested many of these sensors, and also we have demonstrated the capability to get water samples. Now, the integration has been quite successful, and however, we have not reached the level of persistence that is required by the oil companies. They would like to stay, to measure continuously the environment. They're talking about many months, if not a year. Consider areas where maybe there is, it's difficult to launch and retrieve vehicles. So for that, in that regard, we are looking at a new concept, and because we want to extend the mission time of the vehicle, and at the same time, we are working with a variety of small vehicles, and we want to minimize the cost. So we don't want to put too much intelligence in the vehicle. So we have decided to design a new device that can download the data and recharge the batteries with minimal vehicle cooperation. So the idea is like a refueling and a data collection device that will connect to the vehicle, download the data, refuel recharged batteries, and the vehicle can go again. So you don't have to retrieve it. The device has motors. Think of it as an ROV that can track the vehicle and connect to it autonomously. And this device can be operated from the surface of the sea, can be a ship, can be even, and probably better, an unmanned surface vehicle that has the capability to patrol an area and refuel all the vehicles that need refueling and download the data when the data are needed. the same device, of course, can operate from a garage on the seafloor, and this is what probably is the solution preferred by the oil company. So you have a permanent fixed installation on the seafloor connected to shore by power and have the data link. This is a picture of the device, which is ready. We are experimenting it, and I think it will be ready at the end of the summer and will be reported at the next Oceans conference. I would like now to conclude sharing with you my thoughts that I believe the single vehicle technology is really mature. Autonomous persistent systems are being studied and realized using multiple cooperating vehicles. I believe, though, that we need to reduce the vehicle and subsystem costs, and we need at the same time to increase the number of vehicles participating to the network, mainly because we want to benefit from the economy of scales. If we cannot do that, I don't think that these tools will be readily used in the future. And of course, we need to have system building blocks for interoperability and for cost effectiveness. And I'm just mentioning a few, like this idea of refueling the vehicle. We need to have tools like the one we are proposing or others that can refuel the vehicle and download the data. We need communication and gateways on the surface for navigation and communication. Of course, we need the development of compact, low-power sensors, chemical, biological, acoustics. We need to improve energy sources, and we need to standardize on control and application software. With this, I conclude my presentations, and I don't know, I'm open for question or if there is time. Thank you.